have, yeah, got it. It's okay. Oh, is it? Oh, no worry.
We got someone from to let us know. So
it's a good thing they noticed it.
Yeah. Okay, let's go ahead and Janet will come.
Okay, so you want to share it?
Yes.
I mean, if you go to
Also. Okay.
Share screen.
Yes. No, it should be this one, I think.
No, it's not this one. So we need to share. I don't think it's this one though.
Ay. No va eso, pues. Okay.
Okay.
Απλά το Vogiatzis μπορεί να μείνει.
Okay. So hopefully it's better now. Yeah. Yeah. So I was saying, yeah. So this is the standard sort of pipeline. You have a neural network that looks at the source, sort of looks at the task frame, and then decides a policy. And then you have a target task, which what you do is you try to auto-encode that. So remember, so this is the task which we assume that we know how to play, we know how to actually execute, and this is the task we would like to execute, we would like to learn. Okay, so the first thing you do is you just auto-encode this. So you basically just grab random frames out of it, random data points, and you learn how to describe them in some embedding. And then the crucial step is you train a discriminator between the two embeddings that essentially learns, it tries to enforce these two embeddings to be statistically indistinguishable. You want to, I think there's some feedback there. Apologies for all the technical problems, sorry. Yeah, so essentially this discriminator, the role is to try to make these two distributions as similar as possible. And it turns out, I mean, sort of a metaphorical way that you can actually see this is it basically learns how to encode both of the tasks in the same language. So for example, if these things are Pong and breakout, it will learn things like, the paddle being the same in both cases, and there's a ball in both of these tasks. There are sort of some similar underlying features. Even though we're not quite sure exactly how the embedding mapping actually works, but we're kind of metaphorically thinking in that fashion. So it's about aligning the two languages of the two different domains. And then now, if you do all of this pipeline, it turns out it's much faster to learn how to play breakout, having already learned how to play Pong. So if you can imagine that Pong is this sort of simpler task that you don't actually, maybe it's a simulation, or it's an easier thing that has less costs for your agent to learn, and the other one is a more expensive thing, in the real world that you cannot afford to have too many environment experiences. Then this sort of thing can actually help you gain time and a whole bunch of other things. Okay. Okay, so on to urban modeling. So a lot of these principles we have actually recently started applying in the domain of urban modeling of urban environments, which, I mean, there's quite a nice motivation for it, because the primary motivation we had was traffic control. So we were interested in training agents to automatically switch traffic lights on and off. But it turns out there's, talking with the actual sort of stakeholders in these city councils and these sort of agencies, there's a real interest in being able to create realistic simulations of an urban environment like a city that actually can perfectly mimic what happens in actual sensors. So imagine you have this big urban model, let's say Nicosia, and then you can actually pick one particular junction, one particular area, and you can try to simulate CCTV footage coming from that node, right? Or it could be, instead of CCTV, it could be air quality measurements. It could be other types of, car flows, pedestrian flows, this type of thing. And it turns out people are super interested because not only you can then try to do downstream training of other agents to control traffic, do transport routing, crowd management, this sort of thing. But you can also think about improving the training of actual human controllers, because a lot of these junctions, a lot of these sort of automated junctions, I'm not sure about Nicosia, but definitely in Birmingham where I live, are actually controlled by humans. So there's actually a physical human there that looks at the situation and decides what button to press. In each case, now I'm going to release this stream, I'm going to release an extra lane in that direction, and so on. So it's very important for a variety of reasons to be able to do this type of accurate, faithful modeling. So how would you do something like that? So we have already begun work in this, generating a few different things. So one example is generating images, which is maybe my primary sort of domain, but it's not the only one. The trick is that you can use a conditional GAN that can actually be conditioned with a graph that can then encode a variety of discrete and continuous variables. And then you can encode things like vehicle positions, colors, types of engine, and so on and so forth. And also time of day, the season, weather patterns, and so on. And compared to, you might have already, lots of people have actually seen generated synthetic images these days, but compared to the way these are generated, what we're talking here is a much more fine-grained type of control. So instead of, just using, for example, a ChatGPT prompt, for example, here you're actually controlling it in a very fine way. And what you need to do is you need to emulate a specific CCTV sensor. So these are not, you cannot just generate an arbitrary view of a city. It has to be mimicking a particular CCTV camera that you have placed in a particular junction. Okay. And then what you do is, at the end, is basically you have the output of a dedicated traffic simulator. For example, in this case we use Sumo, but there are others as well, that you can use essentially as an underlying sort of latent explanation for this traffic scene, for this world scene. And then what you do is you map positions of cars and all other types of output of that traffic simulator. You map it onto a realistic view. And now when you do that, of course, because it's all finely controlled, you can actually change things like time of day, you can change weather conditions, you can make it winter, summer, you can have snow, and stuff like that. And we even have a little tool that you can actually use to manually place cars where you want them. Okay, so this is a very weird type of setup, right, for generative modeling, because we're actually trying to emulate a specific camera. So we're not, just generally trying to draw cars on streets. It's a specific camera, and you can observe it as much as you like, but then you need to be able to somehow explain it using a latent, the Sumo sort of output. Sumo is a traffic simulator for those that are not familiar. And then from that, you can then do reinforcement learning to control the cameras. I'm not going to go into too much detail of this. Is already it's already quite well established, and we can actually show easily that it outperforms most of the existing sort of smart camera infrastructure, like induction hoops and stuff like that. We can also do knowledge transfer. We can try to apply. We can actually try to learn the task of controlling in one junction and then map it onto other junctions or map it onto different weather. This knowledge transfer is huge in this whole domain, because it turns out if you can control one junction, you can actually control many other similar looking ones as well. And, of course, we have evaluated this. What we're doing now is we're actually building an evaluation with Coventry City Council. And I think a lot of people are quite anticipating what's going to happen there, because We just need to show the first application. In all of this, we have never really properly controlled an actual camera ourselves yet. And this is going to be the first time we do it. And by the way, nobody else has done it globally. So if we're the first, that's going to be quite cool. But it's not just about images. I'm also interested in other types of simulation, and people actually generally these days are really interested in things like air quality, understanding how air quality is affecting, how air quality can be manipulated, can be controlled, can be improved, and so on. And we have really good modeling methodology that can really predict very well both traffic patterns as well as air quality. But what is less successful is in capturing the correlations between the macro model of air quality and the underlying sort of micro models, things like traffic, individual cars, basically, right? And the problem with that is that this makes it very hard to answer what-if scenarios. So I don't know about Cyprus, but I think in the UK at the moment, all the rage is all about ULEZ, these ultra-low emission zones in cities. Everybody wants to know, in every city wants to know, can we have a ULEZ? Is it going to help? Is it going to make things better? Is it going to make things worse? There's a huge bunch of policy decisions and trade-offs. And people would love to know, policymakers would love to know the effect of these particular experiments. What would happen before actually doing it? And it turns out with existing methodologies, it's quite tricky to do that. But it turns out with the techniques that I'm talking about, you can use essentially the same idea of trying to use the sumo output, the simulation output, as a latent variable, and then latent variable of observed traffic flows. So you can actually try to map what happens in a sumo frame to the actual measured traffic flows, using vehicle click-through rates or click counts and stuff like that. So you can actually try to map what happens in sumo, which we know is not perfectly accurate. It's vaguely correlated with anything in the real world, but you can try to map that onto the real world as using it as a latent variable essentially. And then when you do that, then you can now map these traffic flows to actual air quality. This is another bit which, in theory, we could automate as well. We could try to put it in our model. We haven't done it yet, so this is essentially more simplistic type of air quality measurements from traffic flows. But now you have that. Now you can actually try to do the experiment. So you can actually see what happens if you introduce a ULEZ zone in this green region. This is actually Cardiff. I think we have somebody from Wales here. Yeah. Yeah, so you can actually see what happens. Is it actually doing things, is improving a few things, but perhaps it's actually making things worse in the vicinity of the low emission zone. And this is essentially just the beginning of this research area. It's quite big. I'm sure there's going to be lots more by us and other people. This is just some of the press that we got from that work. BBC covered us and a few other people. And as I mentioned, we have now a trial underway. Everything is all set up. We have the hardware and everything for 3 junctions in Coventry with Coventry City Council. But our aim is really to be able to do full city models. And this is something that at the moment is out of reach. We cannot really do it. There's a few different challenges, in fact, and I'm actually putting together an EPSRC bid with Imperial to try to tackle this thing exactly. The main thing is the multi-level granularity of simulators. So as you can imagine, I don't know if you imagined it already, but when you're trying to simulate a whole city and you say, I want to know what's happening in a particular junction, and then somebody else says, okay, now at the same time, I want the simulation of what's happening at that other junction or at that whole area of the city in terms of traffic flows and in terms of air quality, perhaps, or any other more macro type of information. You need to make sure that all of these levels of simulation are consistent, right? And it turns out this is not a trivial problem. So the best thinking about it says that you kind of need to have almost independent sort of world models that are modeling each of these levels, but then you have to have a separate layer of trying to enforce consistency. I mean, it's a very nice open question. We can maybe discuss it later. Yeah. So I mean, I hope that from all of this analysis, there's a few patterns that are coming out and things that we can maybe extract as at least, mental principles that we can keep. As I said, we're not close yet to proper mathematical theory. That's the goal. But one of the things that we definitely know is that the key use is domain expert knowledge. So if you don't include somehow very, very strongly enforce the existence of domain expert knowledge into your data synthesis, you're not really going to achieve much. Essentially, all you're doing is you're rearranging pixels. But I still believe that this is the key, essentially, to making all of these technologies, machine learning and AI, much more democratic, much more accessible to everybody, aside these sort of big industry giants, as I said. And eventually, I think that machine learning and AI engineers have to really see themselves not so much as developers of new generations of models, but essentially agent coaches. I mean, I really believe in this idea that your goal is really going to be all about developing and devising the most efficient training regime, or which can be either a set of training tasks or an actual handcrafted data set that you create for a particular task using your expert knowledge. I think this is essentially going to be a much more scalable solution to the problem of AI, as opposed to what is essentially the current thinking, which is these huge autoregressive models that we train, and we just hope that they learn some correlations. The real world is not really like that. That's the main take-home message I want to leave you with. The real world is based on these small, isolated micro problems for which data is very, very hard to find. And if we can somehow enable these people to use machine learning and AI, I think we will have made a very big step in a much better, more democratic sort of set of technologies. So that's all I had to say. Thank you very much. I'm happy to take any questions. Yeah.
Thanks very much for the great talk. I mean, you said you talked about a lot of things, so I had questions coming up in my mind. So now I will say something. I don't know what. So when you showed the slide with the TSNE and the synthesized data, for example, I mean, the way I understand this is that, we're doing what seems like interpolation in the two-dimensional latent space, but in the output space, it looks like extrapolation to us, right?
Mm-hmm. Yeah.
And what I was thinking is that obviously, you've shown that you can control the generation, and all these things. But I'm thinking in general, the role that diversity plays into this, it's matter. Like, so data might look scarce or sparse, or they can look huge, but they're huge, but they actually don't have a lot of modes of variability, right? So they're just, the variance is the same.
Sure.
And I'm saying this in conjunction with some papers that I've seen that kind of say that, in certain cases, when you use data augmentation, you actually cause the model to perform worse.
Absolutely, yeah.
And, there's this so-called model dementia thing, idea. So basically, I guess my question is, what's your take on that? I mean, do you have any insights or?
Yeah, absolutely. We have seen this as well. I mean, no matter what you can do just by rearranging pixels, which is, in a weird sense, this is kind of what that particular model seems like it's doing. You can only do so much. You can never hope to get anything out of distribution, for example, right? But this is essentially why the human input is important. I mean, basically, you need to have a human expert that really understands the underlying methodology, the underlying sort of shape of that manifold, how that hollow space looks like. And of course, I know what you're going to ask now. If you have that expertise, then why do you need AI, right? I mean, you just use that human and ask them whatever you want to ask them. Well, that's true, but deep learning and AI is still useful even in those domains, right? And I'll give you another example, which is one I've also worked quite a lot recently, which is monocular depth estimation, right? So I give you an image, try to extract depth. It's an inverse problem, blah blah blah. Deep learning seems to be able to solve it. And you might ask, why do you need deep learning in this case, right? It's basically, a fully understood geometrical problem, right? Matching pixels gives you depth, right? What do you need deep learning for? And we still use that. I don't think there's any good name for it yet, but it's what I would call algorithmic deep learning. I don't know if there's any good way to express this. It's basically areas where we use deep learning because it's very, very convenient. It's the fact that we can deal with missing data. We can actually very easily encode all types of priors, all types of high level things. And something similar happens here. There's a lot of these tasks that you have a human that already has a pretty good idea of how they work. Yeah. And if that is the case, then you exploit that person. You just ask them to answer specific things for you, design specific things for you, and you ask them, and you use that as a downstream model. But it would never work, for example, in a case where we don't have that. So if you literally are faced with something completely unknown on the frontier of biology, for example, you're trying to classify something that even a human is not really certain exactly what is going on here, then that's not going to work there. There's not going to be any real shortcut in that situation other than like doing the hard work, labeling as many examples as you can.
Or hopefully using foundation models nowadays.
Yeah, exactly. Yeah.
I see what you're saying. I mean, I agree. It's actually, I would say that it's like, taking that person that knows everything and transforming them into the inductive bias of your algorithm, right?
Yeah, precisely. Exactly. Yes, exactly. Yeah.
Right. Thanks very much.
Yeah. Thanks.
Yeah, okay. So thank you very much. So it was very interesting. I'm not really expert in computer vision and all this. So it's just a couple of very generic questions. So at some point, I think in a couple of actually slides, you mentioned something about introducing physical models and simulations in this, especially in the in your last example.
Yes.
Can you elaborate a bit more on that? I mean, how do you see this incorporation of this compared?
So, for example, the classic one is this case here, the air quality one. So there's many. And I think I mentioned it here. Here, one of the challenges for urban scale urban modeling. The thing is, physics. I see physics as essentially another type. I mean, by the way, not just physics. It's physics. It's statistics. It's logic. It's a whole bunch of these sort of, let's say, hard facts. Yeah, that. Any algorithm that really wants to do this, really wants to synthesize data sets, they need to be aware of that, right? They need to be aware, they need to be, fully adhering to the laws of physics and the laws of, primarily the laws of logic, right? So you need to somehow be able to encode them. Now, the current sort of perceived wisdom there is that the way that you do it is essentially in a generative way. So you have your physical simulation that is, like, custom built and you trust it, let's say weather patterns or whatever, weather simulator, whatever, and you try to learn from data points that are created from that simulator. But the way I see it and the way that I'm trying to write it in this proposal I'm writing, I think it's we need to do it in a higher level than that. We need to somehow interpret physical laws. When I say physical laws, I mean don't think about anything crazy. I mean, it could be as simple as Newtonian mechanics, right, in the beginning, right? And there's already a few papers that begin to do that. In the last ICCV, I saw quite a few people that were going in this direction, trying to interpret. Yeah.
Sorry, because it's a very general question. And actually, we are working on this field as well. Do you have something specific in your mind?
Yeah, one of the specific things, for example, is
how you are going, for example, to incorporate here the model about, the physics-based simulation about air quality, for example.
So what we can do fairly easily is we can actually, maybe learn in an autoregressive way, right? So learn a foundational model of weather patterns, for example, or air quality, the correlation of air quality to traffic flows. Yeah. So you can actually essentially let sensors just capture data for you ad infinitum and then try to see if you can learn it. So that's one way it can be done. What I want to do is I want to see if I can create a neural network that interprets laws in some higher level. I'm being vague because this is something that's quite difficult, right? It may be easier to try to understand it with things like logic, which I keep coming back to. So you would like your, let's say Newtonian mechanics, right? So you would like to have a model that is almost constrained to be able is almost constrained to produce scenes and frames that automatically adhere to these laws of Newtonian mechanics, right? So you cannot have accelerations that, violate fundamental laws of physics. You cannot have. So this is kind of the way I imagine it. So somebody sitting there and handcrafting a neural network architecture that by definition, by construction, adheres to these laws. That would be one way. Of course, ideally, what I want to do is I want to be able to say, to something like a ChatGPT type thing, here's a textbook of Newtonian physics, go and learn it, and then, make sure that.
Much different thing. Yeah. Okay. Okay, thanks. We can, just if I may add more, just on curiosity. So what are the computational demands for all this calculation? Do you need to use a machine, a large-scale machine?
So far, no, because so far we have been really focusing on up to, I think, four simultaneous junctions. So
use GPUs,
yeah,
supercomputers.
Exactly. So something is like a small scale GPU server with, I don't know, 10, 20 GPUs is perfectly fine for training much of these things. We're not talking, we haven't really gone to the stage of the full scale sort of foundational or, world model type thing. This is where we want to go. And this is where, we're going to start using, some much bigger, much larger computation facility, especially when you want to model an entire city. Nobody has really properly done that. I mean, of course you can simulate, Sumo can easily handle Cardiff, for example, but doing this sort of multi-layer consistent simulation, it's just too complex. But hopefully we can do it. Yeah.
Now I have to ask a question. So in the computational modeling part of the work, Yorgo, I didn't quite understand, of course, the applications are very new and interesting, but methodologically, what is the new element is there something new about how you do that modeling, or?
At the moment, what I'm after is the overall underlying principles, right? So some of the things that I quite cheekily I put in the little blurb that I circulated, that's the real goal. So understanding when what is the mathematical theory that underpins this. When does it work? Which cases does it work? Without doing it, can you predict if it's going to work for your case? That's the main thing I'm working towards. We haven't really, we're not there yet, but we can already start to see the principles, right?
I think my question was about the part where you showed that you have already done the simulation work, the computational model.
Yeah. I mean, for example, in this case, in the case of the image generation, the novel bit was controlling the generative modeling using graphs. That was the novel bit. Nobody had actually done an architecture like that. There's a few different challenges, obviously, right? Because everything's geared towards images and conv-nets. But I mean, we didn't invent graph neural networks. Somebody else did. I think with a lot of the stuff that we do, it's all about tweaking existing architectures and applying them to different strategies. This is also quite interesting. I'm afraid I cannot really. It's actually in submission, but what is also interesting here is the way that we do this mapping from Sumo output to traffic flows, because essentially we're using something like a cycle gun. So it's ampered data transformation. You have a whole bunch of Sumo frames, a whole bunch of actual real traffic flows, and you're just essentially using this this mapping from one to the other and from the other back to the first to align the two spaces together. That's also quite new. Nobody has done that. Yeah, I mean, it's bits and pieces. I mean, I wouldn't say the real thing that we're working on is this sort of global mathematical theory of data synthesis. And there's quite a few very important questions around there. But I would be, we haven't solved it yet. Thank you. Thanks.